Thanks for the nice introduction. Thank the organizers for inviting me here. It's my great pleasure and honor to speak in this wonderful workshop. Today I'm going to talk about regularity and the dynamics for some nonlinear diffusion equation on bounded domain. So this is the equation. Dimension bigger than or equal to 1, omega is a smooth bounded domain. And the nonlinear diffusion is ut equals Laplace u to the power m. And we impose zero boundary condition on the boundary. And this is in general called the post-median equation like Ben talked about yesterday. But here we focus, we suppose the initial data is non-negative, so the solution will be non-negative. So we only consider non-negative solutions. So our concern is the regularity and the dynamics of non-negative solutions. Okay, so in many literature, so by the way, the m is a positive number except 1, because if it is 1, that's a heat equation. In many literature, the nonlinearity u to the power m is put under the Laplace. But for myself, I like to put the nonlinearity on the time. Okay, this is just a personal belief. Okay, the reason is because my academic origin was in the study of Yamabe problem, so we usually like to put the u to the power p not on the Laplace. Okay, so when p is bigger than 1, it is called the fast diffusion equation. So why is it called the fast diffusion equation? Because it has the so-called infinite speed of propagation like the heat equation. So if you give me an initial data that is compactly supported, then the solution will be immediately positive. And it diffuses very fast so that it has the so-called finite time extinction phenomena, which means after finite time, the solution will be vanished. And it has a special solution in the form of separation variables. If you let u equals ftgx, then you can do the separation variable, and you can find such a special solution. Okay. So it's the t star is the vanishing time minus t to the power 1 over p minus 1. P is bigger than 1, so the power is positive. And S satisfies this semi-linear elliptic equation. And we concern with the regularity and the asymptotics when t goes to t star, the vanishing profile. So when we're studying the vanishing profile, because it vanishes, so usually we have to normalize it. So it's not vanishing, but it's bounded and below by something, right? And we also need to rescale the time to infinity. So this is very commonly used scalings. So we rescale the t star to infinity, and we normalize u to v, like u divided by this vanishing rate will be v. And that v will satisfy a new equation. It's very similar, but it just has one additional term on the right-hand side, u to the power v to the power p there, the same p. Okay. And when p is a Sobolev subcritical, like p is strictly less than n plus 2 over minus 2. And in a very pioneering paper of Berryman-Horan, so they studied this vanishing behavior. So they assumed and conjectured the regularity of the solution up to the boundary, and then they show that the solution indeed converged to a steady solution along a sequence of time. And from the nowadays point of view, this is not very strong conclusion. The convergence only along a sequence of time. But if you recall, at that time it's 80, and if you look at the time the written is 1978, that was even before the resolution of Yamabe conjecture, and not on top of the Yamabe flows. So it's also before Leon Simon showed the convergence of the negative William flow. So at that time, the maximum they can do is along sequence of time. And if the steady state, if the limiting profile is unique, then you have the convergence. But unfortunately, in general, it's not. So at that moment, this is indeed the best they can do. Now, and then since then, so there were two questions remain. First, can we prove this regularity? And second, can we show the convergence without assuming this regularity? So there's a regularity assumption quite strong. Essentially, it's like a C2, C21, like in time, so along up to the boundary. Okay, so now let's talk about the regularity part. Okay, so as I said, this is we consider non-negative solution, and because in infinite speed propagation, it is immediately positive inside. So it's inside, it is positive, so it's uniformly parabolic. So inside, it is smooth. Right? So the difficult part is on the boundary because u equals 0 on the boundary. And if you take the derivative inside u to the power p, you will see singularity near the boundary. Okay. So in 83, Sachs and Benedetto, they show the convergence, the continuity up to the boundary. Okay. And a few years later, Chen and Benedetto, they show the other continuity up to the boundary. The difference is that 83, they use the parabolic scaling, and in 88, they use the intrinsic scaling. So we obtain the holder. And a few years later, the Benedetto, Kwong, and Vasbury, they further show the Lipschitz continuity in the spatial variables. They show that the solution is bounded, so it's comparable to the distance function. So that is was the regularity before. So in the joint work with my collaborator Jinggang Xiong, we had 2 papers on that. So for any p bigger than 1, less than infinity, right? And we consider use bounded non-negative solutions. And t is extinction time. Then if p is an integer, then it is smooth up to the boundary. If p is not an integer, we always can differentiate in the time variables, and all the time variables are C2 plus P in X. So 2 plus P means the integer part of 2 plus P, and then the fractional part of that. And this is optimal in the sense that if you look at the separable solution, right, the regularity in X is the same as the regularity of the elliptic problem. But we know S is like a distance function. So if P is smooth, or if P is an integer, we always can take derivatives. So it is smooth. If P is not, up to some point, we cannot take derivatives. So it has to be C2 plus P. So you can do this in one-dimensional case. So it is C2 plus P. Oh, in general, okay, to save space here. So C2 plus P means C.
Why do you?
Oh, no, this is 2 cases. If P is an integer, then it's smooth.
Yeah.
If P is not, it's not smooth. Because you cannot take infinite many times derivative on the right-hand side. If P is 2.5, you only can take 2 derivatives. And that is the square root of the distance. You cannot take a derivative. In 1D, you can do the expansion. Okay. So this is the regularity part. Now how about the asymptotics? So when P is still Sobolev subcritical, later, so Friso-Simondon in 2000, they finally showed the full-time uniform convergence using Leon-Simon's method for the convergence of negative Coulomb flow. You have to use the Lojashevich inequality to show the full-time convergence. Okay. The reason is one difficulty is that the limiting is the stationary states when P is bigger than 1 in general is not unique. So if you have many possible limiting profile, you don't know which one you would go, right? So that we needed Leon-Simon's infinite dimensional version of the Lojashevich inequality. And then Bonforte, Grillo, Vasquez, they show the so-called relative error convergence okay. in 2012. So without knowing higher order regularity, this is a non-trivial improvement because we are dividing something close to 0 on the boundary. Okay. So The first is error convergence, and the second one is the relative error convergence. At that time, they only know the Lipschitz continuity, so this is non-trivial improvement. And then, of course, its interesting question is, what is the convergence rate? So Bonfante-Figali in 2021, they showed the generic exponential convergence. The gamma can be made optimal, which I will mention a few slides later. Okay. Generic means if you give me a domain, I perturb a little bit, it will be exponentially convergent. We will see a little bit a moment later why. And Bonfante-Figali, they use the so-called entropy method, and Agagi provided another proof using the energy method. And Choi and McCann says they showed the higher order asymptotics. Okay. So we know the limiting profile, then what are the next order terms, for example. Okay. So our regularity implies the convergence in more regular norms. Otherwise, it's just the relative error and infinity norm. But if we have the regularity, of course, we have the convergence in higher regular norms. Okay. So this is a story for the faster diffusion equation. Okay. So once we made our paper in archive, one day I received an email from Xavi. He asked me, hey, Tianling, would you prove work for P less than 1? So we didn't thought about that, and I said, okay, let's look into that. So when P is less than 1, it is called the porous media equation. Okay. And this is a slow diffusion, which means if you give me initial data that is compactly supported, at least for a short time, the solution will still be compact supported. So it has a free boundary. Just slowly diffuse. Okay. It also has a separable solution. Okay. So if you plug in the FDGX, you can have a separable solution. And this is, it has a very, very nice name called friendly giant solution, named by Darbert Koenig. The solution looks like a constant t to some power. The power looks the same, 1 over p minus 1, then times s. S is still a solution to this elliptic equation. Okay. And now p is less than 1. So the power on t is negative. So when t equals 0, it is infinity. So this will bound any initial data. So by the comparison principle, any solution will be bounded by this giant solution. So that's what we call friendly giant solution. And when p is less than 1, this semi-linear equation has unique solution. There's a difference between p bigger than 1 and p less than 1 in the elliptic level already. Okay. And so the solution is Holder continuous. And then in 81, Arison Pretier proved that although it is it has a free boundary, right? But after a waiting time, the solution will be positive everywhere in the domain. And then after another waiting time, the solution will be Lipschitz, okay? And then it will be comparable to, of course, it is bounded by the friendly giant solution and bounded below by a shift of the friendly giant solution. Okay. So a consequence is that if you divide a u on both sides, you subtract 1, you can see that will be bounded by c over d. So this means the solution to the porous media equation will converge to the friendly giant solution with the rate of 1 over t. And this 1 over t is optimal because you can start with a shift of the friendly giant solution and you converge, then you will, the rate will be 1 over t. So that's sharp. And a consequence, this is, so it's still very similar to the Benedetto quantum vast-free result for the fast diffusion equation is Lipschitz in X. By the way, I want to say again that so there are two waiting times. The first waiting time to make the solution positive everywhere in the domain. And the second waiting time, it will be comparable to the Friendly-Giana solution, comparable to the distance function, that is Lipschitz. Okay. Now, indeed, these two waiting times in general will be different. Okay. We have really counterexamples to. First, it's not Lipschitz, although it's positive but not Lipschitz. And then another waiting time will become Lipschitz. So, so the work with Chevreul-Sauton and Jinggang say that if we consider this porous media equation, then after waiting time, the solution will be smooth in the time variable, and in the x variable, still again is C2P. Okay, and this is also optimal by the Friendly-Giana solution. You can see that because we cannot take a derivative on the elliptic equation. And furthermore, we show that there exists a tau star such that if you shift the Friendly-Giana solution to tau star, then indeed this U will converge to this shift of the Friendly-Giana solution with a beta rate, 1 over T1 plus gamma. Gamma is strictly bigger than 1. So which means that so the Friendly-Giana solution is not optimal choice in the end. It should be a shift of the Friendly-Giana solution. And then the converge to that one is much faster. Okay? And so in general, we don't know how to quantify this gamma, but in one dimension, we know that we can take gamma equals 1. We are not saying that's the best, but we say gamma can be 1. So gamma equals 1, it is true in 1D. Okay. So this is for the porous media equation. Okay, now let me say a few words about the proof strategy. Okay, of course, we are posing this theory for weak solution, but for us, we prove a priori estimate, and then by the way, posing it, so the solutions are the same. Okay. Now, what is the difficulty for the regularity? Okay, now we look at this equation, right? U to the power p, take a time derivative equals Laplace u. If you take the derivative out, it's p u p minus 1 u d. And we know U is comparable to the distance. Okay, so U over distance and D to the power p minus 1 ud. Okay, so distance, if the boundary is flat, it is like a xn direction, which is nice. Okay, and then we can think of U over D as the coefficient of the equation. And we know that U is comparable to the distance, so U over D is bounded below and above by 2 positive constants. But if we want to bootstrap, the missing part is the Holder continuity of the coefficient, right? So to bootstrap, we need U over D to be Holder. U over D to be Holder is the gradient Holder estimate, C1 alpha estimate, which is unknown, which was unknown. Okay, so this is like the Holder estimate of the ratio of 2 solutions near the boundary. So how to show this Holder regularity? Okay. So as I said, so we have 2 papers for fast diffusion equations. So the first one we did is for the Sobolev subcritical and Sobolev critical. We didn't know how to do Sobolev supercritical at that moment because our method. Okay. So what we did in the past at the beginning is okay. So we consider this equation. Okay, we define a so-called curvature-like quantity. This is similar to those in geometric curvature flows, right? You define some scale curvatures, you write down the equation of the curvature, use the maximum principle, then you obtain the estimate for the curvature, then you obtain property for the solutions. So analogous to the Yamabe flow. So we define this curvature-like quantity, and we define a norm of this curvature, this MQ. And then we write down the equation for MQ, which will be a nonlinear ODE, and then we use estimate, eventually estimate for ODE, we show that this MQ is bounded for any Q less than infinity. And then what we can have is by some Holder inequality, so eventually we get is VT over V, any LQ norm is bounded. So we call this higher integrability regularity. So why this is useful? Okay, because what we want is we obtain a priori estimate, right? So we take the derivative in T, not X. Why? Because if we take a derivative in T, the structure will be kept. But if you take a derivative in X, only tangential one is fine, but the normal one will be not. Okay. So if you take a derivative in time, boundary is still 0. At least that is kept. Okay. So, and then we take a derivative in time, then you will have you have a equation for VT, right? So VT, you think of a linear equation for VT, then you have the coefficients. So we learned from Degenerate model for the linear equation, if there are drift and a zero order term, you need some integrability for those lower order coefficients so that we can run the Degenerate model, like Ln or Ln over 2, that's for elliptic. For parabolic, maybe it's Ln plus 2 over 2 and Ln plus 2, right? So we need some high integrability condition which is not available. So this way will help us get the higher order integrability of the coefficients of the linearized equation, then we can put a strap. Okay. So in the proof of obtaining the boundaries for MQ, we used Sobolev inequality. But that's the reason why we only can get to the Sobolev critical exponent. If it's supercritical, then we don't have Sobolev inequality. It's gone. Okay, now the second method. This was our second work. So we use a different approach. Okay. So what we do is, okay, we pick a point in omega, and let the G be the green function at that point. Okay. Again, remember, so inside is already smooth. We only need the regularity near the boundary. Okay. And then, so this green function will be like distance, comparable to the distance. Then we think of the ratio. W is U over this green function. Okay. So U satisfies the equation, and of course, W will satisfy equation as well. So the equation for W is still nice in the sense that it only has 2 terms. Of course, you can change the green function to other possible functions as long as it is comparable to the distance. But for those, maybe you will have 3 more terms. Right? But if we choose the green function, the equation for the ratio still only has 2 terms, which is nice, in my opinion. So we choose this green function. And the goal is to hold the estimate of this ratio W near the boundary. Okay? And then we use Degenerate iteration to prove that. So of course, to use Degenerate, we have to build up all those necessary ingredients for this procedure, like Sobolev, Poincare, scaling, and so we have to carry out all of them. Yeah. It's quite long, but I think all here are experts on Degenerate, so I hope we are convinced we can do Degenerate here. So that's the second that's the method 2. Okay. So that's for the regularity. Now let's talk about the convergence. So the convergence will be treated in 3 different cases. First is subcritical, and then critical, and then supercritical, which is nothing known. Okay, so here today I'm going to talk about the dynamics or the asymptotics in the subcritical and the critical case. Let's look at the subcritical first. So P is less than n plus 2 over n minus 2. So once we have the regularity, and then we can use the Loyarsevich-Simons technique to prove the convergence. Although it is not negative gradient flow, strictly speaking, but we can do it. Okay. So the Loyarsevich inequality says if you have a Hamiltonian, and first of all, you can show that this Hamiltonian is decreasing, and the difference between V and the limit will be bounded by the gradient of F. And the interesting is you can do it 1 plus gamma. Gamma is strictly positive and less than equal to 1. 1 is the best one you can get. So whether gamma equals 1 or not, So whether gamma equals 1 or not 1 will have a difference in terms of the convergence rate. So if gamma less than 1, the convergence rate can only be improved to be algebraic, polynomial convergence. And if gamma equals 1, the convergence will be exponential. Okay, and you may wonder, hey, so in what case would it be equal 1 or not 1? Okay, so there is a sufficient condition saying for every non-negative solution of the steady equation, okay, the linearized operator at the solution has a triple kernel. So, like in Bonforte-Figali's paper, they prove generically the convergence is exponential because this property holds generically. That's why the exponential convergence holds generically. Okay. Well, I said that this is only sufficient condition. Okay. So there's another condition which is slightly weaker, the so-called integrability condition, saying that the kernel can be non-trivial, but the kernel has to come from the solution itself by taking some derivatives. And furthermore, Choi and McCann says in their paper, they also prove that the relative error converges either exponentially with a sharp rate or decays algebraically at a rate of 1 over t at least, or slower. Okay, so the optimal algebraic convergence rate is still unknown. Now, how about the higher order asymptotics, right? So before the regularity was known, then the argument for this, you have to, to make the rigorous, so that's why many pages could be needed. And however, once we know the regularity, we can do the higher order asymptotics like the heat equation solving by Fourier series. Okay. So you have the diffusion, nonlinear diffusion equation. We know it converges to a steady state S. Okay, now S is the limit. Now what we want to is what is the next order term, error, right? So you do the difference, right? Let's say H is the difference, the error. So we write down the equation for the error. Of course, the equation, the leading terms would be the linearized equation. There would be an error term which will be quadratic. And then the higher order asymptotics will be dictated by the spectrum of the linearized operator in proper weighted L2 space. I can do this quickly here. So then how to find the spectrum of this linearized operator? Okay, so S is a steady state. We can rewrite it as, the left-hand side, you think of this is a linearized operator. You plug in S there, and right-hand side will still be this. So from here, you can see that S will be a non-negative eigenfunction. So therefore, 1 minus P is the first eigenvalue of this linearized operator. And now, when P is less than 1, 1 minus P is positive. So we know the first eigenvalue is already positive. Okay? So the convergence rate will be dictated by this 1 over P, the 1 minus P. Okay? So all the eigenvalues are positive. The next order term after this asymptotic limit is still S, because S is the first eigenfunction, is the leading term of the error. Then in dimension equals 1, we can find the second eigenfunction. In high D, we don't know what is the second eigenfunction. Okay? So in dimension 1, we can show the second eigenfunction is this, because this is a solution with some lambda here, and this only changes signs once. So this is the second. Oh, the spectrum is in a weighted space. And when P is bigger than 1, now the first eigenvalue is negative. And that is a little bit complicated, right? If the first eigenvalue is negative, you may wonder there will be 0 eigenvalues or not. Right? Okay. So the non-degeneracy, as I mentioned before, to a sufficient condition for the exponential convergence, saying that linearized operator is invertible, which means there will be no 0 eigenvalues. Okay, then the next positive eigenvalue will be the sharp convergence rate. But what if there are 0 eigenvalues? Right? And those zero mode can dominate the convergence. If this 0 eigenvalue dominates, will lead to the algebraic convergence. So that's the reason why there will be, the non-degeneracy makes a role here. So it's the spectrum of the linear operator, whether there are zero eigenvalues or not for the fast diffusion equation case. If the Proximity equation, the first eigenvalue is already positive, so that's relatively easier compared to the fast diffusion. Okay. Now, in the last moment, I want to talk about the critical case. So it's a critical case. You can think of this as a Yamabe flow on the bounded domain. But one difference is that this is a post-unbounded domain with zero boundary condition. Okay. So if we consider the Yamabe flow on compact manifolds, which was proved by first Hamilton, right? The Ru-Gang-Ye on locally conforming flat case, Stewart-Switlake for dimension with small energy, small initial data, and then eventually solved by Simon Brandl. So they show the convergence of the Yamabe flow on compact manifold. So the solution is uniformly bounded, eventually converge. But here, it's post-unbounded domain with zero boundary condition first, and so the equation has some degeneracy. Second, the solution could blow up if the domain is star-shaped. Why? Okay, the reason is that if it does not blow up, the solution will be uniformly bounded, then we can use relativity to show the convergence. If the converge, will converge to a stationary state. But if the domain is a star-shape, there is no non-trivial solutions by Forhozawa identity. So that's a contradiction, so which means the solution must blow up if omega is star-shaped or convex, for example. And in 2002, Galachinov and King, they consider first the radial case. Okay. So omega is ball. Then the solution will be radial. And then they can use asymptotic analysis to show that it blows up. The infinite norm will be comparable to square root of t. Okay. And of course, in the bulk, there are simplifications, like use radial, using ODE, and also if the solution blows up, it must blow up at the origin. Okay, so in 2022, Yannick Xie, Junchen Wei, Yongquan Zheng, they constructed solutions that it blows up at the finite remaining point in general domains with this blow-up rate using the Green method for parabolic equations. So they construct solutions of blowing up at there are many places could blow up. But the rate is always square root t. Now, of course, our goal is to classify the asymptotic behavior, so how it blows up eventually. And why and how it will blow up. So the reason is because this is Sobolev critical, we know it has a family of solutions which are usually called bubbles. The solution is of this form. Cn is just constant, so that it makes the equation here the constant is 1. And then this form. A lambda bigger than 0 is a free variable, and A is the center of the bubble, which is also a free variable. So it has a family of solutions. Right? So if lambda going to infinity, there are infinity norm going to infinity, so it will blow up. So these are the enemies, and these are the only enemies to us. So we don't know how high the bubble is. We don't know where the center of the bubble located. So these are the we have to figure out. But here you may wonder, hey, this is a global solution, right? How about make it to the bounded domain with zero boundary condition? You do a projection to the H1 space. Basically, okay. On the boundary, you set the value equals the bubble, you do the Poisson extension, you subtract it to make it boundary equals 0. Okay. Because originally this is not vanishing, so you have to make the 0 on the boundary for us. So you do the projection to make the 0. And so before that, Jingang and I did a modification of this critical fast diffusion equation with the so-called Brigitte-Nirenberg effect. We add a zero order term here. This B is bigger than 0, so that it will help us. And this is less than the first eigenvalue of the Dirichlet eigenvalue of the Laplace, so that the operator is still coercive. Okay. And this, we know the Brigitte-Nirenberg, with this, it will help us to show the existence of compactness. And then here, we can show that the solution it will be uniformly bounded and it will converge to limiting states. So in this case, the solution will not blow up. Okay, so that's a modification of the Yamabe flow. Of course, that's not the ultimate goal, right? The ultimate goal for us is the Sobolev critical fast diffusion equation without any other term. Okay, so what do we do? Okay, and what are the enemy? What are the difficulties? So again, as I mentioned before, we define this scalar. This indeed is a scalar curvature. This time in the past, this is P, but here P is n plus 2 or n minus 2. This is indeed a scalar curvature of the conformal metric. And then, so we can derive. So because of our regularity result, so we can take a derivative of R. And then we can derive the equation of R and use most iteration. We can show that R actually converges to 1. Okay, first. And the second, if R goes to 1, and we know that R satisfies this elliptic equation, minus Laplace V equals R to the V, the critical power. So we know by a result of Stewart, along any sequence of T nu going to infinity, along a subsequence of any sequence, okay, V can be decomposed as this. This is a summation of M bubbles. V infinity will be a stationary state. Okay, so let's continue here. So along a subsequence, V can be decomposed as a summation of the bubbles with the stationary states V infinity. And the V infinity solves this equation. V infinity could be 0. May not be 0, which is also possible, so we don't know a priori. The convergence in H1 0 down. So at this moment, we are only able to deal with the case that here the limit you have possibly have m plus 1 terms, right? So m is unknown as well. So at this moment, we are only able to deal with the case that the m there are m plus 1 terms here. We are only able to deal with there's only one term, either V infinity or only one bubble. Okay, I will make it rigorous in a moment. So if we can show that if the solution converges to a positive V infinity along a sequence of time, then the solution will converge uniformly to it. So if converge along sequence time, it converges to it. That's not surprising. We have seen this from the Loyasevich, right? And second, if the energy of the initial data, which is the Sobolev ratio, less than or equal to the 2 bubble energy, then the solution blows up at most at one point. And furthermore, if it blows up, then it is V infinity must be 0. So if we have this assumption, then we can show that either there is only one V infinity and m equals 0, no bubble, no blowing up, or V infinity equals 0 and there's only one bubble. Okay. So the assumption will simplify the problem a little bit. So what we can do is this. So if the energy of the initial data is less than 2 bubble energy, then V converges either to a stationary state or the relative error of V and a bubble will converge to 1. Of course, this converges to a bubble, and with polynomial convergence rate. And furthermore, we can quantify the lambda. Okay, so how lambda glues. Okay, so the lambda glues like t to the lambda glues like t to the 1 over n minus 2 power. Okay, and recall, so the PU, the infinity norm is lambda to the n minus 2 over 2. So eventually lambda will glue like a square root of t. So it's consistent. Okay. So we can quantify the glues of lambda, and we also can show the convergence of A will converge to a point interior, not on the boundary, interior with some rate. That's not as important as lambda. Okay. So at this moment, we are working on multiple bubble case, which is a little bit more challenging and more complicated. So in the last few minutes, briefly show the ingredients of the proof. Okay. So first, we use the convolutional L2 weighted space. V is a solution. Okay, V so depends on time. So, and then we can decompose L2 into three spaces. One we call this quasi-unstable, which is the span of the bubble itself. And then quasi-central space is the derivative of the bubbles in A and in lambda. And the quasi-stable, which is the left. And you may wonder why, okay? Why we do this? Well, this is motivated by the eigenvalue of the linear operator at a bubble, a standard bubble. And it's the classical result. The first eigenvalue is negative. You have n plus 1, 0 eigenvalues, and the next eigenvalue is positive. The kernel is n plus 1 dimensional, this linear operator. Okay, now recall that we have this equation. R is the scalar curvature we defined using the Laplace V. Okay. So Vt satisfies this equation. Okay. And because under the energy assumption, V only blows up at one point. So the convergence to stations is just easier. We just consider the blowing up point case. So it blows up only has one blow up point. So V is like a bubble. Sorry, there should be a P here. There should be a P here, the projected bubble. And but we don't know. We don't know so we only know it's the convergent bubble in the energy space, right? So we decompose V to the alpha T times this bubble plus W. W is error. And so how to determine W? So W minimize this L2 weighted norm. Okay, and right. So by the implicit function theorem, for each time we have A, we have lambda, we have a W, and A lambda smooth in T, so that we can take a derivative. So we differentiate V using the ODE of V. So we have the ODE for alpha A lambda, and then we project this derivative of V into this n plus 1 dimensional quasi-central space, because in that case, this n plus 1 central space will dominate, and the others are small terms. Okay. And then we have n plus 1 for Zava identity. We have n plus 1 ODEs, and we have n plus 1 for Zava identities, so that we can do the estimate. Thank you.
Questions, remarks? If you think about an elliptic equation and you look at the dynamic behavior when you modify P, then at some point you see that you cross over from having a unique solution S to multiple solutions S. So you can think about this as like a bifurcation going on. And can you understand something about the type of bifurcation, if this is a pitchfork bifurcation or something similar? Because you're already studying the spectrum of the linearized elliptic equation, so you could possibly see that how the eigenvalues change when P changes.
Okay. Apparently, so the borderline is 1. Okay, the linear case is a borderline. So, okay. The short question is, I don't know the bifurcation, but it's clearly there's a phase transition, right? So linear case, and P less than 1, and P bigger than 1. So these are three different cases. So P less than 1, there's only one steady state, and the eigenvalues are positive. And when P bigger than 1, there could be 0 eigenvalues, or there could be not. And by the way, you asked me one question yesterday about the stability. Like we have the convergence, right? So if you perturb, because when P be bigger than 1, we have multiple steady states. And one is about the stability of the limiting behavior. And indeed, there are stable profiles, and there are non-stable profiles as well. So what is the stable profile? Okay, here, right? So this is the equation. So when P is Sobolev subcritical, we can show the existence of solutions by variational and compactness, right? So we define the energy, you find the minimizer. And the minimizer is unique, okay? And if the omega is annulus, there are multiple solutions. Okay? As long as it's not minimizer, in the annular case, there are unstable solutions. Okay? And it is an open question, okay, regarding the uniqueness of this equation on convex domains. Okay? So annulus, no uniqueness. Well, I'm talking about P bigger than 1. Okay? Annulus, no uniqueness. Okay? And even with only a few results are like 2D, we know that the minimizer is unique. So the solution set even in 2D is not known for convex domains. And this is a long-standing open question.
Just a quick question I might have missed it at the beginning. What is the regularity that you assume on the domain omega?
Smooth.
Smooth, but what do you mean by smooth?
Okay, so because once we have the gradient holder, we have to prove the smoothness, we have to take a derivative. So we have to flatten the domain, right? So there will be an A there. So when we take a derivative, we need a derivative of the coefficient, which comes from flattening the boundary. So for simplicity, we always assumed the omega is smooth, the boundary is smooth. The local graph, it is smooth graph.
But what do you expect in case you assume less regularity on the boundary? Do you have any
I have been asked several times, but it's a good question. We didn't explore. So we used the method of flattening boundaries, so there will be Aij there. So we take the derivative, and we needed the Aij to be smooth.
More questions, remarks, complaints, insults? No, this is not the case, so we thank again